All right. I'm going to do the same thing with the slinky now. Probably use smaller masses. It has a smaller moment, a smaller spring constant. So right now, its initial position, and I'm just going to make down positives because that's the way my meter stick is right now. So my initial position, 19.6 centimeters. I'm going to take my 100-gram mass. I'm going to add it. And now its position. Now, that last coil, and I know most of you can't see it, the last coil is at an angle like this. So I'm going to measure the bottom and the top and just take the middle. So the bottom of that last coil is at 98.2, and the top is at, sorry, that was 88.2. And the top is at 83.3. 82.2. Is that what I said? No, 88.2. And what's the middle of those two? 85.75. And that's with a 100-gram mass on it. Let's figure out what the spring constant is, because I know that negative K delta X is equal to mg. It's an equilibrium. Technically what I'm doing here is I look at the forces I set down as positive and have mg minus K delta X is equal to 0. That's really the starting point. mg equals K delta X. It's a one-dimensional problem. Delta X is plus or minus.
Wait, how is it mg negative when you move it to the other side?
I move the K delta X to the other side.
No, like, so on the top and then the second one.
Wait, what? From here to here?
Yeah.
Yeah, wouldn't mg be negative?
Yeah.
Because you're subtracting
Ignore that first one.
it.
Yeah, technically, that's positive, so weight is acting down. I should have had a negative over here,
Oh, okay.
doing it that way. So we end up with K being 0.1 times 9.8 divided by whatever that difference is. 0.6. Minus 20. 6.5 meters. Okay. So what is the spring constant?
0.6481 newtons per meter.
All right, 6481?
Mm-hmm.
Okay. We have the spring constant now. I have the 100-gram mass on there. If I pulled it down and oscillated back and forth, what is our period? Well, I know that my period is 2 pi times the square root of m over k, which is 2 pi times the square root of 0.1 over 0.6481.
I got a 1.48 for the constant.
Yeah, so did I. 1.4815 if you want to.
And again, that makes some sense. Because my top is 0.98 divided by a smaller number, it should be something bigger than 1.
Point 6324.
All right, so we have a prediction of that, so my period should be about 16 seconds for 10 oscillations. I guess, bad wording. The time should be about 16 seconds for 10 oscillations. Let's see how close we get. Not gonna really put much of an amplitude on it because it's hanging so close to the ground there. All right. Slightly off the ground. All right, here we go. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do we got?
19.0.
19 even.
Anyone else? So that would give us a period of 1.91 seconds. Why are we off by 0.3 seconds? That's not just physics demonstration.
Is it because it goes too low for too long?
No, that's not the issue. There's a fundamental assumption we made that is much more pronounced here. That is the badness, the wrongness, the inappropriateness of the assumption is much more prominent here.
Isn't that as ideal?
We assumed an ideal spring. This is not ideal. It has a mass. Its mass apparently more significant than before. So how do we offset that? Well, we need to figure out what the effective mass of the slinky is. So I'm going to take my mass off. And we're just going to oscillate the slinky. We have something I can erase. I know the period is 2 pi square root of m over k. If you ever get confused by m over k or k over m, because sometimes some formulas have one, some have the other, just if you think through it, the more mass I have, I would expect it to take longer to move. So as the mass increases, the period should increase. If the spring constant gets bigger, in other words, it's stiffer, it's going to snap back faster, so the period should drop if k gets bigger. So this is going to be 2 pi times the square root of my effective mass of just the slinky divided by k, which should still be the same, 1.4.
815.
1.4815. And so now we just have to figure out the period of the slinking. As I pull it down, need my timers again. You there? Anyone still need a little extra time?
There.
All right, 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do we have?
11.44 seconds.
11.01.
11.09.
0.03.
Now, I can't just throw out one I don't like, the one that's different, because if I'd done that on the first one, we would have thrown out the one that was closest to it. If you want to, if one seems really odd, it is acceptable to throw out the highest one and the lowest one, if you want, but we'll just take it as is.
11.12.
So the period for one cycle, or the period, is 1.112. So therefore, what is the effective mass of the slinky?
Question. How does the K remain the same?
It's still the same coil. The slinky hasn't changed. The spring constant is based upon the coil, the elastic medium itself, not on what you attach to it.
But we use the mass to find it though. Okay.
We used right, we used that mass, but in theory, if we had used 200 grams, it would have stretched twice as far and the ratio would have been the same.
Okay.
So, what is the effective mass?
4.52.
One more time?
4.52.
4.52. That does not seem right. Yeah, that can't be right. Yeah.
I also got that.
What'd you get?
I also got 4.52.
Did you guys do it?
Did you divide by 2 pi?
Mm-hmm.
So that divided by 2 pi gets you some small number.
I got 0.021.
That's not what I got, dividing it by 2 pi.
All right, on your calculators, did you do 1.112 divided by 2 pi?
Oh wait, I know what I did wrong.
Because if you did that, you divide by 2 and then you multiply it by pi.
Zero point zero 0.046.
0.046.
Yeah. No,
Oh,
no.
wait, 17698, is that what you got?
771.
Wait.
But my
0.046.
average was also
There you go.
0.046, which is what he was trying to say.
All right, so what's the right answer? Oh, it's, which one?
He was trying to say
I got
0.046,
32.
but you wrote down 0.00. But I also got 0.046.
You got point. All right, let's see what makes sense here. So that's roughly 6, so that's roughly 0.6 or 1/6 times roughly 1.5 times 3 halves would get me basically about 0.25, which is about a quarter. If I squared that to get the effective mass, which would be about 1/16. 1/8 is 0.125, 16th 0.0625, so that's closer to my crude estimate.
Yeah,
Okay,
I got
yeah, now I got
0.046.
0 point,
All right, so we got, seem to be a groundswell for that one.
I don't know, that's, yeah. I got 0.
Joseph, are you still getting the same thing?
917.
What are we still,
Solving for effective mass.
okay, so the number I gave you was the effective mass.
Yeah, I assume that's what they're giving me.
I think they're,
Oh, I divided them.
It's okay to say, hey, they're wrong. The wolves that raised them were into the arts.
Still not a difference.
So you did
This, divided
that,
this, yes.
okay.
Then I squared it, to get rid of, square it. Then I times this side by this number to
Yeah, that's the correct process. And what did you get?
I got 0.0377. It also could be, you know what, I bet.
I did make a mistake when I did my
No, but
crude
Laura's
estimate though.
using an average of,
I did the average that was already in my calculator, when you average down all of the numbers, it's 1.128 seconds. Which might be why I'm getting a different number. I don't know, let me just.
no, but
check.
that's the right average, cause I re-averaged it, and it was
Let me give him a
11.1.
calculator.
I'll do it. I thought we were getting by now. It's not that.
Crudely around 1.04. I did make a mistake when I did it. We're just getting close to that. Anyone else still getting 0.046?
With what, the numbers you gave, yeah.
With these numbers, but that 11.12 is wrong?
I got
No,
0.021.
0.0.
You have it,
So you
right.
got that one.
That's what I just got.
Wow.
I just got the 0.46.
Oh my god.
So now we got that one.
Can you just do it? Can you just do it? It's been
How
like
about
10
you do it?
minutes.
Put
Please.
us out of misery, please.
do you want to see what I?
Confirm
I
her today,
think-
but
have
the average,
So if you do it with the one.
All right.
1.112.
So first,
It is
11.44 plus
0.46.
11.07
I just did it wrong.
plus 11.01 plus 11.09 plus 11.03. Then I divide that by 5 and get 11.148.
what?
What?
Oh, no, that's definitely
What?
wrong.
This right here?
That's not what I
This should be
got.
11.128.
128.
Yeah, it's supposed to be 1, 2, 8.
Yeah.
You
lost
definitely
count.
You lost it.
That's
Yes.
again?
Yes.
All right, I'm gonna go ahead with that.
Okay.
All right, so I have 1.1128
I got 11.
divided by 2, divided by
1.6.
3.14159, and I get 0.177.
Yeah.
10777, then I square that. And then I multiply times 1.4815. Oh, wrong calculator. Times 1.4815. I get 0.046.
Finally. I will take your answer. I'll just go with that.
Yeah,
Robin, is that what you got?
Yeah,
0.046.
yeah.
Okay.
0.0465, I think if you take it a little more.
Yeah.
All right, so that is the effective mass of the slinky, which means that when I added the 100-gram mass and oscillated back and forth, the mass underneath is not 0.1, but 0.1 plus the effective mass of the slinky. Therefore,
Still not.
go for a different color, just the contrast here. So the period under the new idea is 0.1 plus 0.0465 divided by 1.4815. And we'll see if we can nail it the first time.
Why are you squaring it? Why are you supposed to square it? Yeah, I did. Yeah.
Joseph, you got what you were doing? Off or or you still thinking you did it right?
Oh,
I did.
I know what I did.
No,
I know what people were doing. If you divide the 1.4815, you get the 0.021. So I was dividing it, but I should have been multiplying it, which gives you the, for anyone who,
I had,
Got
okay,
the
for
point.
the time, I have 1.976 seconds.
I also got that.
Okay.
And we had,
we're good.
19.2,
That was by itself.
19.0.
We got.
that is what we got experimentally, compared now to that, we are considerably closer.
Oh no.
We're about 3% off. You got a different number?
Y'all got 1 point.
I need to just go.
1.976 is what I heard.
I'm not kidding.
Okay, hold on, 'cause I'm tripping so hard.
Oh, that's what I.
Oh, I know what it is.
So the moral of the lesson is make sure you show your work.
For real. Well, we can show work, it's about the calculator, apparently.
If I know what the numbers you meant to plug into the calculator, at least then I can go, okay, that was a calculator error.
Oh, there we go, okay.
Okay, any other questions before we get to probably with the biggest aspect of this?
We got more.
Okay,
No.
There's too much.
All right, one more thing. We have a formula for the period of something to obey in simple harmonic motion.
Goodbye.
But there are situations which are things which are close to simple harmonic motion, but aren't quite. So if I take a pendulum, so this is the fulcrum, this is the point that's not going to move, and then I have a mass hanging at the end of a string of length L, and this mass is gonna swing back and forth. If I look at the forces acting on the mass, I got weight acting down, I have tension acting